We shall continue our discussion on the weld decay. I had shown in the previous lecture that when you weld a stainless steel, intergranular stress corrosion cracking does not occur adjacent to the weld fusion zone, just immediate vicinity of the weld fusion zone, there is no decay, and it occurs away from the heat affected zone. I am sorry, it occurs at the heat affected zone, which is away from the fusion zone. This is a kind of welding done on a stainless steel used for I think this is wrong, actually this is 304 stainless steel weldment, and this is 316 stainless steel weldment is carried out. This is the kind of welding that people do to make the structures actually, okay. And you can see that this is the fusion zone, you see this fusion zone here, okay, and immediately next to the fusion zone you do not see any kind of weld decay, okay. And but if you just move away from the fusion zone, you will get if you move away from the fusion zone in the heat affected zone, you see kind of problems that you normally you get in this actually. Again, this is not a L actually, it is containing 316 stainless steel. Yeah, very close to that, you do not really see any kind of weld decay. This is kind of recapitulating what we saw in the morning. We looked at the various weld techniques in the morning, and we said that the sensitization behavior of a given stainless steel could change based on the welding technique for a given composition of the stainless steel. That is basically happening because of what? Why does the different technique would lead to different sensitization welding technique? It is the heat input given by the welding techniques are different, and so the extent of sensitization differs in depending upon the welding technique. The other important factor that is required to be understood is the thickness of stainless steel we call a sheet. Suppose you want to weld the thickness of the stainless steel plate, a sheet. Now, if I go for a thicker sheet or thicker plate, if I want to weld at one go, right, if you want to weld at one go, the amount of heat that is deposited per unit area is going to be quite large, isn't it? You are going to build up layers, right, we build up layers, and so the more amount of heat is now deposited onto the unit area, and so it takes long time to cool. When it takes long time to cool, then what will happen? Then it is possible that the cooling rate is lower than the critical cooling rate required to avoid the sensitization. So that can be depicted by the simple schematic diagram of time versus the temperature for sheets of different thicknesses, they are welded at one go. Okay, I use thickness 1, thickness 2, thickness 3 and thickness 4. I have little bit, I have just enlarged, it is not going to be that wide actually, okay, I just enlarged for convenience to make it. Now can you tell me in this case what order the thickness is increasing? From the right, the thickness 1 what represented here is the least thickness, the thickness 4 is the most thick one, right. In practice we need to weld the thicker plates, the thicker tubes, in a nuclear industry for example, the tubes of 1 inch at above thickness are welded. Now you are going to deposit heat more, but you need to avoid sensitization, right. How to do that? How do you avoid sensitization in that case? You understood my question? You cannot avoid, I mean you cannot say that all the time I have only thin sheets, I have to go for thick sheets, right. So if you are going for thick sheets and you want to weld, how do I avoid sensitization? How do I avoid it? Can at least some guys have already taken a welding course, right? Yes, it's a good answer, right. So you do not deposit at one go, you deposit once, you continue the layer, allow it to cool, then what do? You deposit the second layer, allow it to cool. So each time when you weld, you are allowing the weldment to lower its temperatures, in which process you are able to maintain adequate cooling rate so that sensitization is avoided. So we do what is called as multi-pass welding. In some cases if it is a tube for example, okay, you want to weld a tube, what one can do? A circumferential weld, right. Suppose there is a tube and you want to weld a tube and you want to weld two tubes, suppose you want to weld them, what you can do? First you can weld and you can have water inside, you start welding, then what happens? Then this gets a good coolant. Not only that, it also builds up nice compressive stresses, okay. So it is in fact advantages for minimizing sensitization, it also minimizes stress corrosion cracking. You will see later that when you normally weld a material, you get a tensile stress. We are not discussing this point here, okay. So there are various ways people weld. In aerospace industries also, they normally cool it using a copper blocks. You can put a copper block and then start welding. The copper block extracts the heat. There are several ways of lowering the quantity of heat and then increase the cooling rate so that you can avoid sensitization of weldments. So these are the some factors which I think is are important in welding of stainless steels. There is one more problem that is concerned with stabilized grade stainless steels, and that problem is called as knife line attack. It occurs in stabilized grade austenitic stainless steels. We talked about two grades of that. One is type 321, the other one is type 347. And in this, what you do in this case, in type 321, it is titanium containing, right? How much titanium you normally add? Anybody remember? It's about 8 times the carbon content is equal to the titanium added. In this case, tantalum plus niobium added together, okay, is equal to 10 times the carbon content. So you can have 0.08 weight percent carbon, and accordingly you can add titanium. You all know that the titanium combines with carbon and no free carbon available. When you weld it, there is no sensitization. But knife line attack is a special case that happens when you weld thick plates. So you weld it. As I told you, thick plates require multi-pass welding, without which you are going to lead to sensitization, right? And in this case, this is any one of that. It could be a 321 or 347. What they found was the attack occurs very close to fusion zone, and into the base metal. So at the base metal side, you will have very close to this, it happens, okay, very close. This is called KLA. Very close it happens. Very interestingly, KLA does not occur in low carbon stainless steels. We need to understand this. And please notice, they do not occur at the regular heat affected zone that happens in a normal 304 stainless steel. It occurs very close to the fusion zone in the base metal. Why does it happen? In order to understand this, you need to understand the thermal cycle, right? If you weld a single pass weld, okay, if you do a single pass weld, what is the thermal cycle for that? Temperature, right? It goes up, it cools like that. Single pass, right? That means but if I have to cover it at one go, okay, and I measure this temperature here, okay, measure anywhere the temperatures, okay, any here or here, anywhere, okay, it of course the highest temperature may change, but the cycle is going to be same. If we are going to do a multi-pass welding, suppose let us assume that this is the place I want to notice here. I am going to put a thermocouple here and I do a single welding, goes like this. If I am going to put one more layer over here, what happens? Again, look at this zone very close to the fusion zone. Huh? This is the first pass, the second pass. In the first pass, when I weld here, when I weld at this location, the temperature goes to very high, maybe around 1200, 1300 may go. It does not melt. Please look at next to the fusion zone, it does not melt, but the temperature goes much higher than the weld decay zone. Maybe the temperature may be around about 1200 to 1400. When I move up here, suppose I start welding here, this location is going to follow something like an heat affected zone for this area. When I start moving up this, somewhere move up, what happens? The distance is sufficient enough for me to consider this as heat affected zone. So this temperature is in the range of what? In the range of this, probably it goes around about 800 degrees Celsius, and this temperature region may be 450 and 850 degrees Celsius. So here it is acting like a heat affected zone for this, because it is sufficiently far away from this location, right. This is the heat affected zone for this, right. If I move away from this, this becomes heat affected zone for this, isn't it? The distance is somehow same, am I right or not? So what happens now? So this is the reason why the knife line attack occurs. Now let us look at what is happening to the metallurgy of this particular weldment in this case and this case. We need to understand stability of the carbides. Cr23C6 is a carbide that forms. What is the temperature region? It is between say 400, 450 and 850 degrees Celsius, right, and is a gamma phase. What other carbides you have here? You also have Cr23, C6 can be there, you can have titanium carbide, tantalum carbide and niobium carbide. Look at this. All carbides. What is the temperature? Around about 1200. Understood or not? The titanium, tantalum, niobium carbides form in the temperature region of 850 and 1200 degrees Celsius. The chromium carbides form between 450 and 850, right? Above 850, what happens to chromium carbide? Dissolves. Then what is happening to titanium carbide and all? Starts forming. This carbide dissolves and these carbides form, and above this temperature only gamma is there and no tantalum carbide, niobium carbide, all these stuffs are not there. Okay? Understood? Now let us look at the weld thermal cycle, right? In a multi-pass welding, what do you do? Is temperature, time, it's not okay. I am going to draw here 1200. It's about 1400. I am going to put it about 1200. Okay. So what is happening here? The stabilized grade stainless steel consists of what? It consists of tantalum, niobium or one of these carbides. They are present in that, right? When you raise this temperature, what is happening to these carbides? They all dissolve now, right? They dissolve. Okay, that is they dissolve. When you again raise it to this temperature, what happens now? This is in the range of 450 and it will be. So what happens now? Suppose you read again, what happens now? What forms? Chromium carbide forms. Please notice in a weldment, okay, in a weldment, I just come back to this place here. In a weldment, this is the melting temperature here, it goes beyond the melting temperature. This place very close weld fusion zone in the base metal does not melt, lower than melting point, but the temperature is sufficient for the titanium carbide to dissolve. In the heat evaporated zone, what happens here? In the so called welding zone, what happens here? Here the temperature is between 850 and 450, but nothing happens because the titanium carbide still remains as a titanium carbide, it does not dissolve, and so chromium carbide also will not form. So here you have no issue, right, here it is dissolves here. When it dissolves, please understand, no sensitization, chromium carbide forms because you are reheating it, by welding process. If you see, for example, if you take 3-to-1, you do a single pass welding, what will happen? There will be no sensitization. Why? Titanium carbide dissolves, but does not mean the chromium carbide forms automatically. That means still the carbon is in solid solution, chromium carbide does not form. So if you happen to weld 3-to-1 single pass welding, a thin plate, suppose you do that, then you have no issue. Because the thick plate, because you are welding at different heights, the lower one becomes interpreter zone for the upper ones, and so the chromium carbide starts forming. So these places the chromium carbide starts forming. When the chromium carbide starts forming, then you get sensitization, and that is why it is very close to this. Please notice, if you move away from it, if the temperature is lower than 1200, nothing happens. Titanium carbide is still stable. So that means you are not going to get any sensitization here nor here, and you get only very close to this. Okay, so that is the reason why it happens. In the thermal cycle, basically the first one leads to dissolution of titanium carbide. The second one, when it becomes the interpreter zone for the subsequent welding, the chromium carbides form, and so it leads to what is called as sensitization taking place, and that is a problem that happens in the stabilized grade stainless steels. It does not happen in low carbon stainless steels because what? Why? Because the low carbon stainless steels, carbon is not there to form chromium carbide at all, and anyway you are going to cool it down. So in the case of low carbon stainless steels, you will not get knife line attack. You get knife line attack only in the case of the stabilized grade, that too when you weld the thick plates. If you do not weld the thick plates, you will not get this kind of problems. Okay. Any questions? Any of you have any doubts?
Why does titanium carbide not dissolve at lower temperature range curve?
Yeah. Titanium carbide is stable, Titanium carbide is stable at ambient temperatures, does not form. See, if you hold the stabilized grade stainless steel at this temperature, what is the likely phase formation? Only titanium carbide forms, chromium carbide does not form. For some reason I do not hold here, I first take it to this temperature, right, I hold it here, I dissolve all of them, then I bring it to this temperature, what will happen? Chromium carbide will form, sensitization will occur. Whereas when I move from this temperature to this temperature, chromium carbide does not form, instead you get titanium carbide or tantalum or niobium carbides, all the carbon is gone. When you lower the temperatures, the chromium does not get enough carbon to form chromium carbides. So this is why the stabilized grade stainless steels or resistance against sensitization, and that is the reason why it is, see why they call stabilized grade stainless steels. The stabilized grade stainless steels are made in this manner. Please note down, you normally hold the stabilized grade stainless steels about 1200, 1250, 1235 depending upon the carbon content, you hold it here. That means in which case all the carbides dissolve, then you bring it down this temperature region somewhere around 850, 900, you hold it here. Then what happens? All the carbon combines to form titanium carbide in 3-to-1, tantalum niobium carbide in 3-4-7, then you cool it. That is the way you use your stabilized grade stainless steels. The stabilized grade stainless steels have carbides. What carbides are they? They are titanium carbide in one case, tantalum and niobium carbide in another case. If they do not have it, then you weld it, you still are going to have problems. Okay. So stabilization treatment means the formation of these carbides in these stainless steels. That is why These stainless steels are always given stabilization treatment. What do you mean by stabilization? Just fix all the carbon so that no free carbon is available for subsequent sensitization process. Okay. So, is it clear actually to you? Any of you have any questions? Okay. So, you should know now the difference between weld decay and knife line attack. Weld decay occurs in stainless steels having higher carbon content, whereas knife line attack occurs only in the stabilized grade stainless steels. The second issue is that it depends upon the thermal history. If you do not reheat it, then what happens? You will not get any sensitization. The third difference is the weld decay occurs quite away from the fusion zone, and knife line attack occurs very close to the fusion zone. There are three distinct differences occurring here. So, these are the important factors. I am going to ask another question to you. Suppose I had taken a stabilized grade stainless steel, it is not very thick, but it is thin. I welded only once, but I am going to apply to a process where the temperature is held in the range of 500 degrees Celsius. The liquid is kept at 500 Celsius. So, what would happen? I have two cases. I have taken 304L stainless steel, I welded only once only, the thin tube. 321 also is a thin tube, I welded only once, only single pass, right. After welding, I am putting to a process where the environment is held at the temperature of 500 degrees Celsius. What would happen to 321 and what will happen to 304L? Please let me know. So, I am going to leave that question to you. You please think over, let us discuss it in the next class. I want you to get into the problem, and by doing so you will understand the basics of weld decay and knife line attack. Okay. These two are important things. So, we have reasonably covered what is called as sensitization and weld decay, and you also know how do you avoid or prevention of weld decay or sensitization. Okay, come on, tell me. How do you avoid it? Low carbon stainless steels. Yeah, 2. Yeah, stabilized grade. For example, 321 and 347 stainless steels. Third, if you can solutionize, if can be done. It is not possible in practice in a structure. You are going to do heat exchanger, and how are you going to do this? But a small, small sections, small components, yeah, it still can be done. Okay. One of the important thing that which we need to consider in weld decay is carbon absorption. So, I have taken, let us say, a type 304L stainless steel. Suppose I have taken this, and the guy has welded, is found nicely sensitized. What he didn't do was, he didn't do degreasing. The surface had some carbonaceous matter, right, some grease or something. You weld it, it picks up carbon quite a bit. So, carbon pickup in low carbon stainless steels are quite easy, it happens. So, you need to be extremely careful in welding low carbon stainless steels. This is process related ones, okay. 2, it also happens in the castings. Suppose I go for type 304L stainless steel casting, and I got a casting, okay. So, very interestingly, the surface sensitized, center looks fine, and as you start moving inside, the extent of sensitization decreases. Please note, it is casting. How many of you are familiar with the foundry technology here? Foundry, you prepare a mold, right, you prepare a mold, in the mold you pour the 304L stainless steels, the carbon content is 0.03 or lower, okay. The surface is getting like this. What do you think happens? If the mold has carbonaceous matter, right, yes, matter, if it has got carbon, right, in the material, right, it can pick up. So, the mold, it depends on the mold, right, so, but that is why it is only on the periphery, not on the center. You can shave off, it can happen, or better way is that go for a like a ceramic mold or something which does not give away the carbon content. So, you see sometimes it is happening, and so you must know how do you tackle the problem. Among all the corrosion issues, two types of problems we have developed extensive testing. One is on sensitization, weld decay, the other one is on stress corrosion cracking. Several types of tests, you will see that, okay. Industrially they are very important. I will be very brief here, and you can always go to the standards and you can read, okay. See, one can take about an hour or so, even more also, because it is a very important topic, but we do not have time, so we will not go into in details about this. ASTM A262 is a standard, and this standard has type A, B, C, D, E and F. So, we have type A, type B, ASTM A262A, ASTM A262B, they call it like that. Various types of tests people do that. Predominantly people use A type A, this is called as oxalic acid H test. You might have done a test in the lab, right? What have you done there? Okay. You have applied, you used 10% oxalic acid, right? It is 10% oxalic acid. You would applied, you made the sample into a anode, right? It is an anode, and what did you do? You looked at the, you applied a current of 1 amperes, right? 1 ampere per centimeter square for about 90 seconds. And you look at the specimen in the microscope, you would have got somewhat similar to the structures. Please notice that there is a magnification supposed to be between 250 and 500, that is the reason behind that, okay. Very low magnification, you might not be able to see grain boundaries properly. Very high magnification, you won't see grain at all, so magnified actually, okay. So you won't see many number of grains, so it is that range it is seen. Now you can see the step structure we discussed already, right, and then the this is called dual structures, and then you have a disc structures. What is the definition of a disc structure, anybody? If you observe the sample in the magnification 250 and 500, at least one grain is completely enveloped with the disc structures, at least one grain completely enveloped. So not necessarily that all of them are completely enveloped, only one, at least one is sufficient to do that. Please do understand, you guys have to be precise in your thing, otherwise if you are going to do some advice with someone, I think it will be really pathetic, okay. You have to be precise in the things. Now this is your disc structure because it is not completely enveloped, I am sorry, this is a dual structure, it is not completely enveloped, the disc structure and this. Please look at, I just wanted to point out one, you may be able to see here, right. Can you see this grain, can you see this here? Similarly, can you see here? What do you see here? What do you see here? What do you see here? Okay, what do you see here? What do you see here? Twins, right? The twins you see there, it is not sensitized. We talked about low angle grain boundary, high angle grain boundary, right? You see that the annealing twins are not at all sensitized, though it is a grain boundary, okay. So they are least sensitive to sensitization. So that is another story altogether. That you can see here also, you can see this, right? You see this, okay. You can see that there is, you see here also, okay. Now this test, what you need to understand primarily, I am not going to tell everything. What you need to understand is what is the purpose of these tests, A, B, C. This one is talks about it talks about only the various carbides. Please notice when you apply 1 ampere, it goes to a very high transpassive region, and so the carbides also dissolve at this particular potentials. And this one talks about acceptable or suspected. Acceptable means there is no sensitization. If it is a dual or disc structure, that means you may do further test with B, C, D, E, F to confirm whether the material is good enough for application. If the oxalic acid H test shows a dual structure or disc structures, you need to do this test actually. Now each of these tests, again there is no time to see here, they are all of different kind. For example, this one we use nitric acid. This is nitric acid plus HF. It is a modified test of this, it is slightly milder. So I want you to people go through this, and these guys, they talk about carbides, they also talk about sigma phases, all this and all kind of things, okay. So you need to be looking at, okay. So in order to, So in order to, so this is very aggressive test, right, sigma phases and carbides and and again chromium depletion region, that is the primary thing in all cases, right. So even if you have a sigma phase, it will start attacking. So they are modified to this test, say D is better than that. So each of them have some reason why people carry out different type of tests. I think you people should when you have time, go through in details and get to know why different types of ASTM tests are carried out. What I would like to focus on here is the quantification of this test actually, okay. Quantification of IGC. Please notice we are talking about IGC of stainless steels only, quantification of this, and we use electrochemical potentiodynamic reactivation test. You might be also doing this if you are not done, okay. This is also part of your lab experience. Now what is the basis of this test? What is the science behind here? The science behind here is you choose an electrolyte that passivates the grains but does not passivate chromium depleted grain boundaries. Please notice this, okay. Only chromium depleted grain boundaries it does not passivate, but that means it is not sensitized grain boundaries as well as the grains, they remain passive, right. So the selection of this electrolyte should be such that this character is given to the electrolyte, okay. Now the electrolyte has got two components, one is sulfuric acid, other is potassium thiocyanate. Potassium thiocyanate is given, right. This one is to passivate, this is to depassivate. Sulfur containing compounds are detrimental for passivation. We have seen it during our studies on pitting, right. So passivate and the depassivate. Now this is a depassivator. If I am going to choose this concentration, very high concentration, it will depassivate everything, grains, grain boundaries and all of them, right. So I need to optimize this concentration. I need sulfuric acid because the sulfuric acid is the what passivates the stainless steel. So the concentration of sulfuric acid, this are optimally chosen, and in this case of stainless steels 304 and all, people use 0.5 molar sulfuric acid plus 0.01 molar potassium thiocyanate. Now how they got this thing? By iteration process. There is no real scientific extrapolation that we can do, all done by sheer extrapolation, sheer iterations to happen, and so they arrive at this particular concentration. For this stainless steel, The same thing is not applicable for duplex stainless steel, nickel based alloys, no, they are not applicable. This is applicable only for the 304 and probably 316, and so you need to change the composition in case the alloys are changed. This is called as the EPR test, electrochemical potentiodynamic reactivation. Yeah, EPR test, okay, EPR test. There are two types of things that people do here. One is called as single loop test. What is done here is I am not describing to you the scan rate and bubbling, all kind of stuffs actually, okay, I do not do that. In a single loop EPR test, what you do is you start, in the beginning you start from 200 millivolts with respect to saturated calcium electrode. From there you come down, okay. So this is how it is done here, okay. This is the sensitized case. If it is not sensitized, please correct the things, okay. If it is not sensitized, you get like this. When you hold it at plus 200 millivolt and completely passivating, please see that here in this case, if you look at the alloy, you may everything passivates, complete passivation. Both grain boundary and grain. But here what happens? Here passivates, grain boundary does not passivate. So the current that is flowing here is essentially due to what? Due to the dissolution of the grain boundary. Now you can calculate the number of coulombs, right? What is coulombs? Current multiplied by the time gives you the coulombs. You know the coulombs of current by integrating this whole curve, you get coulombs. Now you know the grain boundary area, then you can calculate the extent of sensitization. So PA is given as Q, the coulombs upon what? Upon grain boundary area, which is nothing but coulombs per unit area, right, centimeter square, right. And grain boundary area, you know, you guys who have done the metallurgy studies, you know how to calculate the grain boundary area. You calculate that from the ASTM grain size number, right. So that is equal to AS five 5.095 divided by 10 power minus 3 exponential 0.347 x where AS sample area for which you get the current, X is the ASTM grain size at 100x. This you might have studied in the, you know, in your metallurgy courses, right. So, you know the grain boundary area and you can find out the Q value and you can find out the PA, okay, and the PA is indication of the extent of sensitization. Now, people use this technique for qualifying materials in the nuclear industries, okay, and I give you some indication of this PA versus PA value, okay, and what you call what are the implications or interpretations that if PA is going to be less than 2, unsensitized. Please notice these are all empirical one, right, there is no fundamental principles in that, no pitting. 2 to 5 slightly sensitized, pitting and IGC attack, intergranular attack takes place. 5 to 15 sensitized, pitting, attack of entire grain boundaries. Greater than 15 heavily sensitized. So, these are in fact routinely used in the nuclear industries to qualify the material for you know applications in the boiling water reactors and all this stuff. This test is a little more complicated. There is one more test which is more simple, is double loop EPR test. This is what you might be doing in the laboratory. This is also called as DL EPR. In this case, unlike single loop EPR where you rise the potential to the passive region and then you bring it to ECAR, the double loop EPR test what is done here is you start from ECAR, you go up to plus 300 millivolts with respect to saturated calorimeter electrode. Then what happens? You reverse the scan, it goes like that, do like this only, this forward, 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 reverse, reverse, and this is called as I forward, this is called as I reverse. Actually, you do not have to know the area of the sample and you can simply use any area and you can plot only current, not necessarily current density, okay. Now, please notice when you scan from ECAR up to this, here up to this point, grains and grain boundary they are all dissolved. Here what happens? Grains and grain boundary passivate, and what happens here? Grains remain passive, grain boundaries depassivate if sensitized. Okay. Now that means this current, if you can integrate, corresponds to what? Corresponds to the dissolution of the grain boundary, and you integrate this one will correspond to the overall material, right. So you do not have to integrate also. What you can do is you can simply take these values, like the degree of sensitization can be written as I reverse I forward is the fraction of this one, right. This gives you the fraction of the grain boundaries that suffer intergranular corrosion. So this is also used as one of the quantitative tests to quantify to what extent the sensitization has occurred. Okay. If there are no questions, I think with this now we come to end of intergranular corrosion and weld decay of stainless steels. Okay. I just want to move on to another type of intergranular corrosion unless you have any questions or clarification to be sought. Let me go to the next important material, which is aluminum alloys. In principle, I think the intergranular corrosion can occur in all materials. Aluminum is one of the material which is very susceptible to intergranular corrosion. Next is your maybe your zinc alloys. You have zinc die castings people use, right, and magnesium alloys also can undergo intergranular corrosion, but those things I am not going to discuss now. We will end our discussions with aluminum alloys because it has got wider implications in industries. Now in aluminum alloys, the intergranular corrosion turns to a different connotation, which is called as exfoliation damage or exfoliation corrosion. Okay, you can call it. You know what is mean by exfoliation, right? When you say exfoliation, what does it mean generally? It's called layer by layer removal, right? It's kind of plane by plane removal kind of things. In aluminum alloy, this intergranular corrosion takes into, and especially 2000 series aluminum alloys and 7000 series aluminum alloys. These two alloys are they are all high strength alloys, right? They are high strength alloys. They are used in the as a rolled sheets, extruded components. Okay, when you roll and then extrude, what happens? You get a special kind of microstructures. This is a montage, optical montage of one of my students, PhD students who worked on this alloy actually. And you see how the grains look at different directions actually, right. This is the rolling plane, right, this is rolling plane, and this is the thickness, right, the thickness, short transverse, and this is the long transverse, okay, long transverse. Now look at the grains now, okay, look at these grains. they are all well elongated, right. I hope you are able to see these elongated grains. Can you see that? Can you see these elongated grains? And these grains are called as pancake. You stack the pancake and you slice it, see at the sides, you see nice, this one actually, it's in fact the pancake only, right. You take a material and you roll it, you compress, several layers are going to be there, right. They call pancake structures. In exfoliation what happens is that these grains just delaminate, just one after another they get removed from the surface, from subsurface, okay. So that is one of the specific problem that happens in the high strength aluminum alloys. Now, why do they really happen? How many of you have studied aluminum alloys, physical metallurgy aluminum alloys? How do you get the strength of aluminum alloys? Aging, right? It is called precipitation hardening treatment, right? You age the aluminum alloys, right? When you age the aluminum alloys, what happens? The excess solutes which are supersaturated, they dissolve and form precipitates. Right? And age hardening is of course a big subject altogether, but to make it simple, the two types of aging are important for us. One is called as a peak aging, other is called as a over aging treatment. What is peak aging treatment? The peak aging treatment is the treatment at which the hardness of the alloy becomes the maximum, the tensile strength becomes maximum, and you over age, you continue the aging treatment or you rise the temperature, you do whatever, the strength falls down, hardness falls down, maybe 10 to 15% or whatever, okay. You normally do that in order to increase the resistance against stress corrosion cracking. We are not talking about right now. I just want to give an idea why you do overaging, why you are losing your strength. You are losing your strength because at peak aging alloy are prone to stress corrosion cracking, and so they do overaging. In overaging, look at this, the precipitates become coarse. You see the precipitate very coarse precipitates, and the grind bounded precipitates also become coarse. These are the grind bounded precipitates you see here, it's very fine, and these are grain interior precipitates are very fine, and so it has high strength. In this case, because of coarsening effect, strength becomes low. Not only that, the composition of these precipitates also change. In this case, this alloy is actually a 7010 aluminum alloy. It is called AA 7010 alloy, and this is essentially what are these precipitates? There are zinc and magnesium precipitates, and certain amount of copper is present here, right? And they are all almost equilibrium precipitates are there. Over here, it has again zinc, a magnesium, and have quite large amount of copper. Okay, so the precipitates become relatively noble here as compared to this. Why? You take aluminum and compare that to magnesium. Magnesium is active. Even zinc also active because zinc does not form a passivation. When you add copper to it, the precipitate becomes noble. So they become noble precipitates with respect to the matrix. In this case, the precipitates become active compared to the matrix. That means they can undergo selective dissolution here. There is no selective dissolution here taking place. So the intergranular corrosion occurs more in the case of peak age alloys as compared to the over age alloys. I hope you understand the point, right? It happens here. Now the problem that happens here is that when they are pancake structures, when they have pancake structure like this, when corrosion occurs on the surface, maybe due to pitting whatever, the corrosion proceeds inside. It proceeds inside like that. It proceeds like that along these things now, right? It can proceed like this also, like this it can proceed like this. When the corrosion proceeds here, it forms, let us say zinc dissolves, magnesium dissolves, what happens now? Now the volume of these products higher than the volume of the metal dissolved, isn't it? Because it has got a hydroxide, all this, right? It is higher. When this volume is more, what will happen now in this case? What will happen? It is going to strain, it is going to lift the thing now, it is going to lift up. Now that means the grain starts opening. There is going to be now internal stresses. In addition to corrosion happening because of preferential dissolution of the grain boundary precipitates, it is also going to exert certain stresses, and so there is going to be delamination along the grain boundaries. The grains start lifting from the material below the subsurface. So it is exfoliates, they delaminate actually. So that is what really happens in the case of these materials. If you want to see how it happens, I can show you a diagram how these guys can happen. See here, okay. Now this is a P-caged, you can see the corrosion has started from the surface, it gone inside, it created so many corrosion products, it got lifted. Please see, this is not corroded, it's corroded, this volume of the product, it got lifted actually. In the overage condition, it does not happen. Why it does not happen? Because the precipitates here are noble compared to this. When they are noble, the precipitates do not dissolve so much, and so the grain boundary becomes stable. So as compared to this, that means exfoliation corrosion occurs only in the case of P-cage conditions. They do not happen in the case of overage conditions because of this particular thing. Not only that, in the overage conditions, one more thing happens actually. You see in this case, if you look at closely the grain boundary precipitates, they become very coarse, they are separated. Look at this one precipitate separated, so that means they are separated now. So there is even when it corrodes less, but even when it corrodes, they are not good connect, so they are not connecting. The grain boundary is not getting connected completely here. Whereas in this case, because the precipitates are very fine, they get connected. Now what happens? So the crack or whatever, corrosion products accumulates, it starts lifting in this case actually, right? It has happened. So because of nobility of the precipitates, because these precipitates are well isolated, the grain boundaries do not continuously corrode and lift actually. So the overage alloys are more stable as compared to the P-cage alloys, okay. So that is the reason why the P-cage alloys are better off compared to overage alloys compared to P-cage, that is the reason why the overage alloys are better off compared to the P-cage alloys. And P-cage alloys so in any case we do not use P-cage alloys for actual application, because P-cage alloys are more prone to stress corrosion cracking. Those days people were using at all. So so it is very essential for us to understand the chemistry of the precipitates and how do they dissolve. So people have done extensive studies on that, and those people who want to do a MTech project or maybe a PhD work, you can read more and understand them. For the time being, it is enough for us to understand that the grain boundary precipitates are very important, its chemistry is very important, and even more important is the alignment of the grains. They are pancake structures, okay, and so they lift it and leading to exfoliation or corrosion. Now there are different types of tests that people do, and one test is called as X code test, okay, and there is also ASTM standard. There is also ASTM standard which is used as a X code test, where you use highly concentrated sodium chloride plus potassium nitrate and plus nitric acid, and you see if it is P-cage thing, and you see the surface is quite rough, and overage is a little less rough actually, and there is a different kind of alloy system that you have. So when you do the X code test, and you can take a cross section and you can see them in the microscope, you see lifting of the grains as I seen in the as was shown in the previous slide actually. Okay. And this test is considered to be very aggressive. There is also modified X-code test, ASTM things are available for you. You can use modified X-code test to do that. Okay. Okay. So that is about the exfoliation and intergranular corrosion of aluminum alloys. There are several factors, the way you temper, the surface hardness, rolling conditions, they also affect the exfoliation corrosion. There are certain good research papers, some of you are interested, you can read them, and otherwise for this course I think it is sufficient for you to know that this is one of the serious problems. See what happens in aluminum alloys, in aircraft industries, how do they join? The aluminum alloys are joined by riveting process. So they drill a hole, right, they drill a hole and then they rivet it using other aluminum metal, right, and this hole, look at this is a hole here, right, the whole hole is exposed. Now the grains are all now exposed, you see the like pancake structure, I hope you will be able to understand it, right. You take a sheet and drill a hole and all these surfaces are now exposed to getting attacked in the horizontally, so they get lifted, okay. And there are very beautiful pictures available. I can't show you here because of copyright problems, but you guys can read and see. It's a very nice illustration of how grain bound attack can lift the various grains up and causing the weakness. It weakens the structures actually. Okay. With this, any questions? Anybody?
How IGC of stainless steel is different from that of aluminum alloys?
Yeah, and okay, it's a very good question actually, right. The intergranular corrosion in stainless steel, the mechanism is different from the intergranular corrosion in aluminum alloys. I did not in fact dwell on it, right. In aluminum alloy, what is the element that passivates? The matrix itself. The major element aluminum itself is passivating, right. So when there is a precipitation taking place, what is the precipitation taking place? What is the precipitation here? The precipitation in this one is what? Is zinc and magnesium. So the passivating element remains in the grain boundary area. So there, basically the matrix passivation does not get affected, but what is happening instead? The precipitates which form on the grain boundary are selectively attacked here because they are relatively active compared to the aluminum here. So the mechanism in stainless steel is the chromium which is passivating is getting depleted, and so grain boundaries are getting attacked, right. Here the passivating element is aluminum, that is not getting affected, rather what is happening, the active elements segregate and form precipitates in the grain boundary, and so they get corroded at all. So it is not the depletion of passivating element causes problem here, it is the formation of the active phases on the grain boundaries causing the problem. So the mechanism in both the cases are different actually. Okay. Any questions? Okay, if there are no questions further on this, and I still given you one problem, please think over it, okay, and come out with the answer when you meet next time. So thank you very much.